class, today we will discuss on the following objectives. The first objective would be to find the differential equations of equilibrium. The second objective would be to find the differential equations of equilibrium under the actions of the dynamic force. And third would be we will solve a numerical example to find out the body forces acting on a continuum. Differential equations of equilibrium. In general, we define a stress at a point, and if we are interested in defining a stress at a point, say this is the point, then this point has to be a very small. In order to achieve it, we tends to define the elements such that delta x, delta y and delta z tends to 0. This means that delta x, delta y and delta z are very small. So let us first find the differential equations of equilibrium in case of a continuum. So in general, the stress, the state of a stress in a body varies from point to point. So in general, if we consider this as a continuum, the state of a stress that is present at this point and the state of the stress that is present at this point will be different. So we define the state of a stress from point to point. In order to achieve it, consider a small rectangular element. So this one is a small rectangular element. So we are always defining a stress at a point. It is difficult to define a stress for a point. So in order to achieve it, we consider an element which such that delta x, delta y and delta z tends to 0. So this rectangular element has the sides delta x. So this one is delta x, delta y, this is delta y, and delta z is the delta z, the small size of a cubical element which is isolated from its parent body. So this one is the body, and we are defining the stress at this point, this particular point, and this point is isolated from the entire continuum. Since in the limit we are going to make delta x, delta y and delta z tends to 0, we shall deal with the average values of the stress components on the each faces, and these stress components are shown in the figure. So in this figure, the every phases will be subjected to three types of the three stresses. One will be the normal stress and two will be the shear stress. So if we take one particular plane, say this one is this plane we are considering, then the area of this particular plane will be delta y multiplied by delta z, and this particular plane is subjected to one normal stress which is this value sigma x plus delta times sigma x. Other would be the shearing stress, this value of shear stress, and this will be the other values of the shear stress. Similar to this plane, if we consider this plane, again this small body, this small element will be subjected to one values of the normal stress which is this value sigma y plus delta times sigma y. The other value would be the shearing stress in x directions, and other would be the shearing stress in z direction. Similar to this, again if we move to the z face, this is the z plane, a plane defined by the z coordinates. If we consider this plane, again it is subjected to one value of the normal stress and two values of the shear stress. So this is the first value of the shear stress, and this one is the other values of the shear stress. Here the faces are marked 1, 2, 3, and so on. So the different faces, as it is a cuboidal, so it will have a total of 6 faces. So the first face is this face. Again, second face is the this face. Third face is this face. Fourth face is this one. Fifth face is this face, and the sixth face is this face. All these faces are subjected to one value of the normal stress and two values of the shearing stress which is acting along the planes. So on the left hand face, say face number 1, the average stress components are sigma x, tau xy and tau xz. So if we consider the first phase, phase number 1 denoting this phase is subjected to a value of the normal stress which is sigma x. The other values of the stress would be this values of the stress which is acting in the y directions, and the other values of the stress which is acting along the z direction. So if we have to define tau xy, then it will be this value. This is tau xy because it is acting in the y directions. If we have to define tau xz, then it would be defined by this dotted line. Why? Because this is acting in the z direction. Similar to this, if we move to the next phase, on the right hand phase, that is phase number 2. So this one is phase number 2. The average stress components are, so the average stress components will be again the one values of the normal stress which is sigma x plus delta times sigma x. The other values will be this values of the stress, and the other values would be this values of the stress. So all the phases, each and every phases are subjected to one values of the normal stress and two values of the shear stress. Let us now define the stresses that are acting on the different phase one by one. So when we consider the phase 1, it will have one values of the normal stress which is this value, and two values of the shear stress, tau xy and tau xz. So which one is tau xy? This value is the tau xy and this value is the tau xz. As the values of the stress varies from point to point, so other phases will be subjected to other values of the stresses. So at point 2, again it will have two values of the shearing stress and one values of the normal stress. So the values of the stress that is acting on the phase 2, the values of the normal stress will be sigma x plus the partial derivatives of the force x with respect to the x axis. The other would be the values of the shear stress and the partial derivatives of the shearing stress with respect to the x axis. The third will be the values of the shearing stress plus the partial derivatives of tau xz with respect to the x axis. So one phase is subjected to again the one values of the normal stress which is this value, and these two are the shearing stress acting on the particular plane that is represented by the phase 2. So this one is the phase 2. Similar to this, what we have done for the x coordinate systems or the x axis, we will have similar representations in the y axis as well as the z axis. So if we move to the phase 3, so this one is the phase 3. Again it will be represented by one values of the normal stress which is sigma y, or we can say it sigma yy. Other values would be tau yx which is the force acting on the y plane in the x directions. Similar to this, again tau yz represents the force acting on the y plane. So this one is the y plane acting in the z directions. Again, the forces that are acting on the opposite phase of what we have actually seen, that is phase 3, the values of the stresses would be sigma y plus the partial derivatives of the force or the shearing force acting in the y direction with respect to the y coordinate systems, the values of the normal stress plus the partial derivatives of the shearing stress acting in the y directions, and the partial derivatives of the force that is acting in the y directions, in the z directions with respect to the y axis. This is for y directions, this is for x directions. So I should say, so this one is x for x directions, this one is for y directions. If we move for the z directions, this is for z directions, the forces acting in the z directions are the sigma zz. So this one is the values sigma z, which is the normal stress acting on the z plane, tau xz, which is again the shearing stress acting on the z plane directed in the x directions, tau zy, which is again the shearing stress acting on the z plane directed in the y directions. Similar to this, on the opposite phase, which is phase 6, so this one is the phase 6, again it will be subjected to one values of the normal stress, which is sigma z plus delta sigma z. The values of the normal stress will be sigma z plus partial derivatives of sigma z with respect to z axis, the values of the shearing stress and the partial derivatives of the shearing stress that is acting in the x direction with respect to the z axis, and the values of the shearing stress plus the partial derivatives of shearing stress acting in the y directions with respect to the z axis. So we have find out the various forces, various stresses that are acting at the different phases: phase 1, phase 2, phase 3, phase 4, phase 5 and phase 6. The next step would be to write the equations of the equilibrium. For writing the equations of the equilibrium, we need the forces. If we are interested in calculating the forces, what we need to do? We need to multiply the values of the stresses. So these are the values of the stresses multiplied by the elemental area delta A. Then we can get the values of the force that is acting, and further we can write the equations of the equilibrium in three different directions. The three different directions are x directions, y directions and z direction. We cannot simply write the equations of the equilibriums in terms of the stresses in x direction, y direction and z direction. We need to find the forces, then only we can apply the Newton's, then only we can write the equations of equilibriums in x directions, y directions and z directions. Now let this small elemental body will be subjected to different types of the body forces. So we can say, let the body forces component per unit volumes in x directions, y direction and z directions be represented by gamma x. The body force component acting in the x direction is represented by gamma x. The body force acting in the y directions is represented by gamma y, and the body force that is acting in the z directions will be represented by gamma y. Now we will write the equations of the equilibriums in x direction. Now for writing the equations of the equilibrium in x direction, again we write the equation in terms of the forces, not in terms of the stresses. If we are interested in finding the equilibrium equations in terms of the forces, we need to multiply the corresponding stresses with the small elemental area which we have chosen. So what are the forces? What are the stresses that are acting in the x directions? First we write the equations of the equilibrium in x direction. So the stresses that are acting in the x directions are this value is the value of the stress acting in the x directions. The next value would be this values of the stress that is acting again in the x directions. Other would be this values of the stress that is acting in the x directions. This value of the stress that is again acting in the x directions. Now on the z plane, this values of the stress that is acting in the x directions, and this values of the stress that is acting in the x direction. So we know the various normal stresses and the shearing stresses. If we multiply by the corresponding area, we can get the values of the forces that are acting on the different faces. So let's take the first stress, that is, this is the stress that is acting on the x directions. So this is the values of the stress that is acting on the x direction on the figure 2, multiplied by delta y multiplied by delta z. So this one is delta y and this value is delta z, is the elemental area. And if we are interested in calculating the force that is acting in the x directions, we will multiply the values of the stress multiplied by the elemental area. Then we have calculated the values of the force that is acting on the phase 2. Next is the phase 1. On phase 1, this is the values of the stress, that is sigma x, that is acting on the first phase, multiplied by the elemental area, that is delta y multiplied by delta z, it is the area. So again we have calculated the values of the force that is acting on the phase 1. Next comes the values of the shearing stresses. Again tau yx, it is the force acting in the y directions, force acting in the by defined by the plane normals in the y direction and is directed towards the x direction. So this is this figure, this values of the stress, this values of the stress multiplied by the small elemental area, that is delta z multiplied by the delta x. Similar to this, again we have the tau yx, again which is the tau yx is how which is this value, this is this value, the values of the shearing stress multiplied by the small elemental area, that is delta z multiplied by delta x. Similar to this, again we will write the values of the shearing stress that is acting on the other phase, which is this phase, and the values represented is tau zx plus differential partial derivatives of tau zx with respect to z multiplied by the small elemental area delta x multiplied by delta y. Similarly, again tau zx, again this is the values of the stress that is acting in the x directions multiplied by the small elemental area, that is delta x multiplied by delta y. The last term is the values of the body force. As the body force is acting on the entire body, these values of the force would be multiplied by the elemental volume. The elemental volume would be delta x multiplied by delta y multiplied by delta z. All these values will sum up to 0 because this body is in equilibrium. If we cancel all the terms, then we will reach to a final equations, that is this values of this value which is represented by the forces acting in the x direction. So this equations represents the partial derivatives of the normal stress which is acting in the x directions. Second one is the partial derivatives of the shearing stress that is acting in the x directions with respect to the y axis, partial derivative with respect to y. The third one is the partial derivative with respect to z. So the values of the shearing force is tau zx. This is the force that is acting in the x direction plus the values of the body force which is equal to 0. So this one is the first equations of equilibrium when we have considered the equilibriums of the forces in the x directions. Similarly, we will write the equations of the equilibrium in y directions and z direction. Thereafter, we will get the three equilibrium equations in the x directions, y directions and z direction. Why three equations? Because we are working in the three-dimensional space. That's why we will have three equations of equilibrium. Now, similarly, equating forces in y directions and z directions. What we have done for the x axis, we will do it entirely same for the y directions and z directions and will equate it to 0. Then we will get the values of the differential equations in y directions and z directions. Again, we know that the shearing stresses are complementary. For that, it is written on the basis of the fact that the cross shears are equal, then we can say that tau xy is equal to tau yx, tau yz is equal to tau zx, and tau xz is equal to tau zx. So we will obtain the differential equations of equilibrium as the first one we have already derived when we have written the equations of the equilibrium in x direction. So this one is the equations in the x direction. On the similar grounds, if we write the equations in y direction, we will get the following equilibrium equations. On the same grounds what we have done for x axis and y axis, if we write the equilibrium equations in z direction, we will come up with the following differential equations in z direction. So we have got altogether three differential equations or the three equations of the equilibrium in x directions, y directions and z direction. This is in terms of the normal notations what we do. The second types of the notations is the index notations. Rather than writing all these three equations, if we are interested in representing the entire thing what we convey through three differential equation, we can simply write it in the forms of sigma ij subscript j. This means that it is all the derivative with respect to the j plus rho is the density and bi is the body force acting in the corresponding direction. So if we are interested in writing all these equations can be represented by a simple equations in terms of the index notation, which is this equations. The advantages of the index notation lies in that it is very compact, and rather than writing such an extensive equations, we can simply write this equation to represent the entire message what we want to convey. Next is when we are interested in finding the differential equations of equilibrium under the actions of the dynamic force. So we will have the terms of mass multiplied by the acceleration. So an additional terms will come into this picture, which is rho times the accelerations in x directions. If we consider the dynamic forces, this is what we have earlier derived. This one was the equations of the equilibrium equated to 0 when we haven't considered the dynamic forces. But if we consider the effect of the dynamic forces, these coefficients, these things would come in the right hand side, which is the rho is the mass per unit volume multiplied by the accelerations in the x directions. Similar to this, we will get the values rho is the mass per unit volume multiplied by the accelerations that is acting in the y directions. Similarly, we will get the rho multiplied by the accelerations that is acting in the z direction. So under the effect of the dynamic forces, we will get the additional terms. So these are the additional terms when we will consider the differential equations of equilibrium under the effect of the dynamic forces in three-dimensional space. Now the numerical example to illustrate what we have studied. For the state of the stress given by sigma, so this one is the state of the stress in three-dimensional space given by terms sigma. So altogether we have total 9 coefficients with us to define the stress state in three-dimensional space. What form must the body force component have if static equilibrium are to be satisfied everywhere? So this is the conditions of the static equilibrium. In that case, the values of the RHS, which is the right hand side, will be equal to 0. And these are the three equations which we have derived based upon the equations of the equilibriums in x directions, equations of the equilibrium in y direction, and the equations of the equilibrium in z directions. Simply what we need to do is to put these values, say sigma xs is this value in this equations, tau xy, put these values of tau xy in this equations and tau zx in this equations, and differentiate it with respect to x, partially differentiated with respect to x, partially differentiated with respect to y, partially differentiated with respect to z, and this one is the body force that is acting on the on a small element. We will get the first equation. So this one is the first equations. Similarly, we will do the same thing in y directions. Simply we will put the coefficients of sigma yy, tau xy, and tau iz in this equations and differentiate it with partially differentiate it with respect to y, x, and z. Then we will get the following equation. So this one is the second equations. Third is, again we will put the coefficient. These coefficients are given in the forms of the matrix. We will put the values of sigma zz, tau xz, and tau yz, and partially differentiate it with respect to z, x, and y, and this one is the body force. Then we will get the third equation, which is represented by this, which is the third equations. And now in the question it has been asked to calculate the values of the body forces. So what are the body forces in x direction? It is represented by b1. Body force acting in the y direction, it is represented by b2, and the body force that is acting in the z directions, it is represented by b3. If we solve these three equations, we will get the values of the body force that is acting in the x directions, which is this value. The body force that is acting in the y direction, it is represented by this values, and the body force that is acting in the z direction, it is 0, because this terms itself is 0. So finally we have calculated the values of the body force that this system has to be subjected if this system has to remain in static equilibrium. So the learning outcome of these sessions are, the first one is that we have derived the differential equations of equilibrium under the static equilibrium conditions. We have derived the differential equations of equilibrium under the dynamic force. Under the effect of the dynamic force, our additional terms mass into acceleration would come into picture. whereas in case of the static equilibrium, the RHS will be equal to 0. Thereafter, we have illustrated through an example how to find out the body forces if a system has to remain in static equilibrium. This is for this session. We will meet you in the next session. Thank you.